Hello everyone, I am Sai Puppala, PhD grad, Southern Illinois University, Carbondale. Today I'm here to discuss about my paper scale, a self-regulated clustered federated learning in homogeneous environment. I will jump onto the problem statement. Before I jump onto what we are trying to solve, I'm just trying to give a little bit brief introduction about what federated learning is. Federated learning has been in the industry from last 6-7 years, and the whole idea about federated learning is to solve the problem of transmitting the secure information or personally identified information from one client to another client in the machine learning training techniques. For instance, we can think about Google Keyboard, where the user data is being stored in the mobile devices, and you train the machine learning model in user smartphones, and you send the model weights to the global server rather than sending personalized text to the server for training purposes. And the reason why they do that is because to give you a more personalized suggestions while texting some of your folks. So that's how the federated learning has been built or emerged in the industry. So it's been used in different applications, for instance, manufacturing, healthcare, or different other domains. It is highly secured, and the machine learning strategies, some of the advanced machine learning strategies, when you implement using federated learning, we consider the systems to be extremely secure, because we are not essentially sending the model itself or the input data stream. We are sending model weights in the whole process. So now when I talk about all this federated learning system or architecture, I call this as a traditional federated learning, because this traditional federated learning has been first implemented using by Google, and after that we have many advancements in the federated learning. Because of that, we have named as a traditional federated learning. There are highly, blockchain technology federated learning, highly secured federated learning, peer-to-peer connection federated learning. There are many advancements that has been done in last few years. So what problem are we are here to what problem we are here to solve, that I will discuss more in details in next upcoming slides. In the problem statement, we can proudly say that we have built a federated learning architecture where the cost has been reduced quite a lot. I will jump onto the numbers in the result section, but yeah, as the slides progress, you will get more idea on what we are trying to solve here. Introduction. As you can see, this is a traditional federated learning. On the right side, if you see, there are a bunch of data sets for each user. The data sets are consumed by the smartphones or edge devices or clients, and you train based on that based on the data, and you train a model and you get a model. Once you get the model, you send the weights from user 1 to the server, user 2 server, user K to server. Once all the weights has been received in the server, you do a aggregation strategy. So the aggregation strategy, the basic aggregation strategy what one can use in server is a Fed average. You can use more advanced strategy like NOAA. So there are numerous different aggregations that you can perform at the central server. So this is a traditional federated learning. There are much more advancements which has happened in the federated learning in past few years. Some of the challenges that you can see from this system is, now that we only have like 3 or 4 in this example, but let's assume that you have 1 million or 2 million clients or edge devices. And in this 1 million, 2 million edge devices, there is only one central server or global server. Think about how many communications that you are sending from each devices. So if one device is sending model weights every 2 minutes, you have 1 million devices which are sending 20 million or 10 million requests every 10 minutes or 20 minutes. So there could be a huge overweight on the server in terms of computation, and there could be a massive communication problems or communication inefficiency in this whole architecture. And to resolve these problems, we have identified this niche gap, and we thought of doing a bit of research on how do we solve this problem of the traditional federated learning. we present a decentralized federated learning where the whole goal is to reduce the overhead on the server and to reduce the communication over communications that is happening between the edge devices or to that of the global server. Now, this can also be leveraged in different other areas where I will talk more details about that in upcoming slides. So the proposed solution is Scale. Scale is a self-regulated clustered federated learning. In the homogeneous environment, we also can apply that in the heterogeneous, which I will discuss briefly about heterogeneous. We are actively working on that in the future papers. So as I mentioned, some of the key features of our system is it is dynamic in nature. It's like once I get into the architecture, you'll probably understand what the dynamic nature represents. And it's hybrid, it's totally hybrid, meaning that it can communicate with the global server, or it can communicate with the driver itself. So some of the questions that you might have when I talk about key features can be resolved, or you'll find solutions when I start discussing about the architecture as a whole. The decentralized driver selection or checkpointing or health status verification mechanism. These are some of the key features that we have implemented in the Scale. Now, this is an overview of how the Scale would look like. So think of it like if you have 100 clients and you have one global server, these 100 clients, we have to find a way. So the goal is to have 10 clusters out of these 100 clients. Let's assume that each cluster has close to 10 clients, and each of these clusters represent similar patterns. We'll explain more into how do we even form these clusters. But the goal is, rather than sending 100 communication requests from these 100 edge nodes, we would form a cluster and we would make one client or one edge node as a driver, and then that driver will send the information to the global server or the central server. In this way, if let's say if you have 100 clients, you would combine that to 10 clusters, and each cluster will have 10 edge nodes. So 10 multiplies 10, that's 100 clients clustered into 10 clusters, and each cluster will have one driver node, and this one driver node will send information to the global server. So to jump into the process of how this exactly works, or how the clusters are formed, we'll jump on to the next slide. So we have introduced something called feature variance, performance indexes, and proximity evaluation in our paper. To give you an example of what feature variance is, I would jump onto the next slide. Feature variance is basically if you have, let's say, the input data for in our situation, in our paper, we have considered the homogeneous. So when I say homogeneous data sets, in our example, we have considered breast cancers. So breast cancer has close to 50 different columns, and these 50 columns, we would consider that schema and data types, and we would try to calculate the feature variance score. So this score will be same for same input data. So let's say if I'm providing 50 columns of a breast cancer data set, that score will be the exact same score to all the data. Even the data could be different, like 50 columns, I could have different data. Some might have 500 records, some might have 10 records, but we are not essentially looking at the data itself. We are looking at the schema and the data types, and you calculate the score based off of the columns and the data types. And once you get the common score, you would send that score to the global server, and global server will consider that score. And it's not the solo factor for making the cluster form. It is also looking for the performance index, and the reason why we introduced performance index is to identify the driver within the cluster. So the performance index can be calculated using multiple factors: the computational ability, energy, the life of the battery, and there are different other parameters that we have included, and you can see there are weights that we have multiplied with. The reason why we have put in weights is because we don't want to give equal weightage to the computation power and the energy, or different other scale, the metrics. So each has different weights, and the weights has been identified based on different repetitions of the experiment, and we have come up with a fixed weights based on the aggregates or stats. But in the future, we wanted to have a dynamic in nature weights where the weights is like constantly update based on the how system is performing. We have used a proximity evaluation. A proximity evaluation is after you consider the feature variance scores in the global server. Now the global server will consider this proximity evaluation, meaning that the lat long will be sent from the client to that of global server based on the lat long. It will calculate the distance. The reason why we have used this code is because the Earth is round, not the straight distance, so we cannot use the Euclidean distance. Or Manhattan distance. So this Harveston distance has been calculated based on the score that equation that you're seeing on the screen. And this calculation will determine which node is closer to the driver node. So once you identify the top 10 powerful clients, you would see what are the closest clusters to that of driver node based on the distance of Harveston. And you assign that 10 nodes or 9 nodes to that of driver, and you call that as a cluster 1. So in the same way we formed that 10 clusters, we formed 10 clusters based on the proximity evaluation. So some of the critical things that we have considered for the performance index is computational capacity, network connectivity, energy resources, reliability, data representativeness, and the security. These are some of the things that we have considered, or the selection criteria for the driver node. And we have provided the algorithm. We call that as a weighted consensus-based selection of the driver node. You can jump onto the paper to know more about the driver node and how we have performed the selections of driver node. See, the driver node is a crucial part in our system because once the driver node is identified, we forward to the next steps to form the cluster. And we also have ranked different other clusters. Let's say if the driver node dies because of the energy drainage, or if because of network connectivity, or because of some other reasons, we always have the secondary driver or the third driver, which can switch back and takes the leader position, and that will send the information to the global server. So once the cluster has been formed, the weights communications will happen within the cluster, and the driver node will be responsible to perform the aggregation strategy. So you can consider that as one cluster one cluster as a traditional federated learning, where each cluster will have a weights exchange to that of driver node, and that driver node will send the aggregated weights of that cluster clients to this global server. So the communication weights that are being sent to the global server are the aggregated weights of the clients within the cluster. So that's what's happening, and we call that as a peer-to-peer weight exchange. And the centralized server, the global server, will have receive the aggregated scores of the local clients through the driver node. And once the global server gets all the weights, you do the aggregation, you perform aggregations like fed average, and then send that weights back to the driver node, and driver node will distribute that weight across the clients within the cluster. For the experiment, we have considered the breast cancer data set, which is been collected from Wisconsin Department of Health. And we have considered 100 clients, and the data is being distributed in such a way that some of the data is identical in nature and some is non-identical data distribution, meaning that the input data is being split in such a way that some clients are getting 100 rows, or some clients are getting 10,000 rows. So it's non-identical in nature, and some clients have identical in nature. So we have performed some results, which I will discuss in next upcoming slides. How different or how novel our scale approach as compared to the traditional federated learning, and based on the metrics, you will probably understand the importance of the scale paper. As you can see from here, this is accuracy F1 score, precision recall, ROC, AUC scores. On the left, you see federated learning. On the left right here, you can see federated learning, and here you can see scale. These are the accuracies: F1 score, precision recall, ROC, AUC. I have laid down from round 1 to round 30, there are 30 rounds which are being performed. And in the round 1, we got the accuracy of 58%, and the accuracy of scale is 46%. And if you look at the round 30, the accuracy, overall accuracy for the federated learning is 89, and scale paper accuracy is 86. Although there is a huge communication reduction, which I will cover in the next slide, the accuracy hasn't fallen much. As you can see, the different F1 precision recall ROC AUC scores remain almost same. The accuracy just dropped like 1% or 2%. This graph represents random clients within that 100 clients which are considered for this experiment. As you can see, the dotted line represents the traditional federated learning, and the green straight line represents the scale. And you can see the graph is been pretty similar in terms of gaining the accuracy over the period of 30 epoch rounds. You can find this information in the paper for more details. As you can see in this graph and on the table on the right side, in the traditional federated learning, after the completion of 30 epoch rounds, we identified the overall communications that has happened within the system is 2,850 for the 85% accuracy. And in the scale paper, we have 235, and the accuracy is about 86%. So the 85%, so the reason why we have less accuracy here that compared to the last slide is because we have a client, one of the client was not updating the accuracy, so the score was little low on this slide. But the overall accuracy for scale is 86%, and the federated learning is 85%. But the range of the accuracy for the traditional federated learning is about 85 to 89, and the scale it was about 83 to 86. So the communication drop, as you can see, it has been dropped at 10 times. That's the primary focus for our research paper, is to drop the overall communication by keeping the accuracy the same. So the goal of our paper is to focus more on the communication efficiency. And as you can see here, the processing latency has been clearly mentioned in this table, that the scale processing time is much more less compared to the federated learning, because the number of communication that's been sent from the client, from the driver node to that of global server is 10 times less. So the overall communications has been reduced, and the processing latency has been reduced overall as well. So this increases fastness within the system. So yeah. In conclusion, we found scale to be extremely reliable, and it's efficient in terms of communication, and to reduce the overall memory problem on the global server. And some of the key benefits, as I mentioned, reduce the overall communication overhead, improving the training latency, energy efficiency, and high learning performance. In the future work, we wanted to refine this more to broader applications like different data sets in the heterogeneous environment, like images processing and video processing and unclustered data, unstructured data. So that's our goal, and also increase the accuracy, overall accuracy for scale paper if we can. So that's been said. Thank you so much. You can find more information in our paper scale. And if you have further questions, please feel free to email us. You can find our information on our paper as well. Thank you for your time today. I hope you guys have a good day.